We're going to go through some naming questions. So this is a sapling chapter 3 question. It has a ring, a former ring, and then it has these groups off of it. Ethyls, like little spaceman, like 4 ethyls and 1 methyl. So in naming nomenclature stuff, the biggest part is always finding the parent chain or the root name, I guess. And if you have rings, the ring always is the parent chain or parent name. So in this case, if I circled this, that is the parent chain root name here. So that would be a butane. And since it's in a ring, we say cyclobutane. Okay. So everything else is just built off of that. And at this point, we need to decide how we want to number it, 1 through 4. And the ideal situation here is to have the most substituents have the lowest number possible, right? So to do that, right, we'd name this carbon 1 because that has 2 ethyl groups on it. And then it doesn't matter which way we grow at this point, because it's kind of symmetrical, 3, 4. So we have 4 methyl groups on 3 different carbons. So the way we do this then, we say 1, 1, 2, 4, tetra, methyl. So that covers the 4 groups, right? So if you have, even if the same substituent, even if the ethyls are on different carbons, are still ethyls. So we say 1, 1, which represents the 2 ethyls, right, on this carbon, 2, another ethyl, another one on 4, right? And there's 4 of them, so it's tetra, right? If it was 2, it would be di. If it was 3, it would be tri. Tetra, ethyl, whoops, my bad. Tetra, it's not methyl. Tetra what? Ethyl. Right? Tetra ethyl. And then our last substituent is a 3 methyl. So we got to decide what order to put these in. Another little trick, you don't di, tri, and tetra don't count. So it's E versus M. So the order would be, you'd put the 1, 1, 2, 4, hyphen, tetraethyl, hyphen, 3 methyl, and then put cyclobutane right here without a hyphen. If sapling gets weird and starts criticizing you about hyphens or commas, let me know and I can give you the points. On a test or quiz, we're not going to be that diligent on whether your hyphen was correct or not. We will be diligent on, right, alphabetizing order and the root chain and things like that, but whether you forgot to put this hyphen here, I don't care. Hopefully that helps. So another question involving nomenclature. This is from the Dr. I'm a Turkey lab. So this is also in chapter 3 in sapling. Good old Dr. I'm a Turkey's lab. It's a mislabeled bottle. So what the bottle says is 2 ethyl dash 2,4,6 tri methyl heptane. What they're saying is this name will get you to one structure, but this is not the correct way to name this, right? So that's what they're saying. They're saying this is not the correct IUPAC name, so give the correct name for the compound, right? So what's the correct name for this compound? First thing you're going to need to do is redraw it, right? So what's your parent name here? It's a heptane, right? So you're going to have 7 carbons, right? 1, 2, 3, 4, 5, 6, 7. All right? 1, 2, 3, 4, 5, 6, 7. So on there they have 2 ethyl. So you put an ethyl group there. They have a methyl on 2, a methyl on 4, and a methyl on 6. And they're telling you this is the wrong name. So let's redraw this. So somebody named this incorrectly. And so I would say, again, what's the longest chain? All right, so we need to find the longest chain. So let's take a second and see if we can find the longest chain here. All right, so the question was, what's the longest chain here? They said heptane, and it's not true. The longest chain here is actually 8. 1, 2, 3, 4, 5, 6, 7, 8. So let's circle that. All right, so we know it's going to be an octane then. All right, so we know the parent name is octane. Right, now we got to decide which way to number it. How we want to number from left to right or right to left. Let's see, which one makes the most sense? Which one gives us the lowest number? Left to right? Left to right going this way or going the second way? Gives us the lowest number of our first substituent. 1, 2, 1, 2, 3. So we have to go this way actually. It's not about the lowest number on like averaged, it's what's the lowest number you can get first, right? So this is the lowest number you can get first. So that's, so if I go 1, 2, 3, 4, 5, 6, 7, 8, my first substituent would be a number 2. If I numbered this way, it'd be 1, 2, 3. So 2 is less than 3. So it's not about the number total being lower, it's about the first, what's the lowest one you could possibly get. The lowest one you could possibly get is 2. So what do we have for substituents? Looks like we have 1, 2, 3, 4, what? 4 methyls. So that's a tetramethyl, right? Tetramethyl. And the numbers are what? They are 2, 4, 6, 6 tetramethyl, and then just move octane right there. So it's 2, 4, 6, 6 tetramethyl octane. That's the correct name. All right, taking a look at they call these a Sawhorse projections, where you see the wedges and the hatches.
Yeah, I mean, they'll never have eight.
We call this a Sawhorse. Sometimes people call these Sawhorses. But you got to be able to take something that's on here and translate that to a Newman projection. All right. So this, you should be able to look at this and realize this is staggered. I'm going to fill in what's there in a second. But if you notice here, how do I know where my eyeball's at? Is my eyeball coming from this way or is it coming from this way? What I usually do is I look at the Newman projection, and this has something pointed up, and so does this. So if my eyeball was looking down this carbon, looking down that way, there'd be something right pointed to the top, which makes it sense here. And then this is like to my left, and this would be to my right. Okay. So let me fill what's in actually on this problem. Again, chapter 3 sampling. This is chapter 3 stuff. SH and H there. BR and OH and then F.
That's CI.
That's Cl. Yep, Cl. Chlorine. Yep. So, if my eye, right, I chose to look from this side, not this side, just because I looked at my Newman projection, and they had drawn the top, this one up, so it just makes more sense to go from this way. Again, use your model kits. You're going to have to start seeing in 3 dimensions. It's not easy. Use your model kits to help. All right, so looking down this, if I rotated this, and right, look there, this would be my left hand. All right, my left hand, this would be my right hand. So now if I picture myself here, we know the bromine's up, right? To my left is the OH. To my right is the fluorine. I go to the back carbon, the H is down, right, in the plane. The SH is on the same side as the OH, it's also to my left. and the chlorine is on the same side as the fluorine, it's also to my right. Okay, so you gotta be able to look at this, vice versa, right? You should be able to look at this and draw me this too. Right? You should be able to go back and forth for either one. All right, but take some time and practice to kind of see, all right, where's my eyeball looking? What's on my left hand, what's on my right hand? So I like to think about what's above my head. We're going to take a look at a question kind of about hydrogen bonding and noting what, essentially is asking what is a hydrogen bond? Do you know what a hydrogen bond is? So this is chapter 3, number 14. And essentially you need so they have a bunch of methanol molecules lined up in different ways. And they want you to do is highlight the hydrogen bonding interactions that are possible, or which ones are hydrogen bonding interactions. So really all you need to be looking for here is places where the oxygen and hydrogen can interact in such a way as, right, they can do hydrogen bonding. Right, so for this first one, right, these two H's are looking at each other. They're both, right, they're both the delta plus side of that bond, right? So this would not be a hydrogen bonding interaction, right? Two hydrogens looking at each other is not hydrogen bonding. Now here, where the electron-rich oxygen with its lone pairs, this would be a hydrogen bonding interaction, right? This oxygen, right, that's lined up where the electron-rich part of one molecule is lined up with the electron-deficient part of another molecule, right? That's essentially dipole-dipole interactions, right? It's hard because we don't usually think about molecules except for like one. So this is just showing us what does it look like if there's two methanols in there hydrogen bonding. Other ones, right? So here, those are two oxygens looking at each other. That's not a hydrogen. That's two electron-rich places. Same deal here. Two oxygens looking at each other. Two hydrogens. Not going to be a hydrogen bond. But here, right? There's an example of a hydrogen bond there between two molecules. So it's really just a matter of deciphering what the question is kind of asking and highlighting the correct ones. All right, taking a look at another naming one. This is in chapter 3 again. So another naming one in chapter 3, not 13, chapter 3. Taking a look here. Again, first step is find the longest parent chain, longest continuous chain of carbons. So let's take a second so you can find the longest chain here. All right, we've come to a consensus here that it is indeed 9 carbons. So I think if I take off up here, loop around, that gets me to 9. Right? Now again, the question becomes, which way do we want to number? Do we want to number, right? So if it's 9, what is 9? 9 is nonane. Nonane. So now we got to decide how we want to number it. Are we going to number from top to bottom or bottom up? We look at the substituents. We want to have the lowest number substituent possible. So top to bottom or bottom up? Bottom up. So we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, and I would suggest you do the exact same thing I'm doing when you do these problems. The easiest thing to do. Now we look at our substituents. So what do we have? We have, looks like, got a methyl, a methyl, a methyl, and then an ethyl. So we have a trimethyl. So trimethyl. What numbers are those? They're 2, 4, 5 trimethyl. And then we have an ethyl at 6, so 6 ethyl. And E comes before M. So I would name this 2, 4, 5 trimethyl 6 ethyl nonane.
But E comes from
Yep, like I said. E does come before M. Good. You guys are all paying attention. 6 ethyl 2, 4, 5 trimethyl nonane. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Yep, there it is. 6 ethyl 2, 4, 5 trimethyl nonane. Right, a problem involving chair structures. So hopefully everybody watches the video. We're going to continue to practice this. But in this question, first I'm just going to draw everything out. Bromine axial, hydrogen equatorial down, chlorine axial down, H equatorial up, axial up, equatorial down. This was an H, this is an OH, axial down, equatorial up. This is a CH3, this is an H, axial up, equatorial down, F and a Cl, axial down, F, equatorial up, H. Right, so you probably notice as you practice this, you should get good at just drawing in the axial and equatorial positions. Right, you should be able to realize, right, if this is axial up, the next carbon over, both carbons right over, will have an axial down position. Right, so every carbon in a ring has both an equatorial and an axial position. Sometimes that axial is up, sometimes it's down. Right. But if you're always up in a ring, you will always stay up. Right? If you're wedged, you'll always be up. Right? You can be axial up and equatorial up. So maybe I'll add another layer to this. We'll do a ring flip once we're done with this question. What would happen if I did a ring flip with this? So what this question is asking though, so this is 27 in chapter 3. It's saying, highlight the groups by clicking the atoms that will sterically interact with the methyl group in a 1,3 diaxial interaction. Ooh, so we're going to have to do a ring flip anyways. Right? Because they're asking us, what's going on with this methyl group? What's that methyl group going to interact with when it's axial? Right? So right now, this methyl group is what? It's equatorial, and is it up or down? Up. I like to think of that's just up. So we're going to do a ring flip. Is it going to change? What's going to change? The equatorial part or the up part? The equatorial part is going to change, right? If you're up, you're always up. You can't, right? That cannot be changed. If you're on top of the ring, you're on top of the ring. If you're on the bottom of the ring, you're on the bottom of the ring. But, right, if you look here, right, this is an axial up, this is an equatorial up, right? You can be up and be either one. But if you do a ring flip, you change from, if you're equatorial, you become axial, but you still remain up. Can't change that. So let's try a ring flip with this. I'm going to just shrink it down a little bit. All right, so the old flip. So that means if we're leaning to the right, kind of like we are here, right? If we lean to the right, in the ring flip, we're going to lean to the left. What else happens in a ring flip? Or if I number these carbons, I'm going to zoom back in and number these. Oops, sorry, that makes it angry. Let's make that carbon 1, 2, 3, 4, 5, and 6. Number your carbons is never a bad idea. So what happens in a ring flip, right? If you think of this as a chair, this is like the headrest of the chair. It gets pulled down. And at the same time, the footrest gets pulled up, right? So these are shifting spots. Shifting spots. So carbon 1 is now here. And that means carbon 4, in this case, is now here. And then you can fill in the rest of the numbers accordingly. All right? We went from the top of the chair, got pulled down, the footrest got pulled up. Right? So now this is the top of the chair and this is the footrest. Right? So now we fill in everything else. It might be just easier at this point to just draw in the positions without even worrying about the bromines, the hydrogens, all that stuff. Let's just draw in all the positions. Right? So just like I started here as axial up, it's just an easy way to start. I'm going to go over here, or you can start here and say, okay, this for sure has axial down. That means it has equatorial up. This would have to have axial up, equatorial down, axial down, equatorial up, axial up, equatorial down, axial down, equatorial up, axial up, equatorial down. So that's just filling in all the positions, axial and equatorial, right? Obviously I'm going to fill these in right now. But we always remember, if you're up, at the end of the day, you're always going to be up. But if you were equatorial, after a ring flip, you're going to become axial. All right, so let's look at carbon 1. Carbon 1 has a bromine. The bromine is up or down right now. Here it's up, and it's axial. So on carbon 1 now, after the ring flip, it's going to have to be equatorial. And the H is still down, but now it's axial. Carbon 2, the chlorine was axial, and now it's going to be equatorial, but it's still down. And the H is now axial and still up. Take a look at carbon 2. The H was axial and it was up. So on carbon 3, the H is still going to be up, but now it's going to be equatorial. And now the OH is axial, but it's still down. That doesn't change. Here, the H was down, so now it's still down, but it's equatorial. And there's our CH3. That's axial and up. For 5, the fluorine was up, and it was axial. Now it's up, but equatorial. And the chlorine was down and equatorial before, and now it's down and axial. For 6, the H was up, and the fluorine was down. Cool so far? For that flip, right? If you're up, you stay up. Ring flip, you change from equatorial to axial. That's what the ring flip does, right? You gotta be able to draw it both ways. Now what the question is asking, and I hit on this too in the review video, is which of these, right? So it's saying for the chlorine, for the CH3, which groups is this gonna bump into in a diaxial interaction? It's a fancy way of saying this group's axial. Who else is axial and up? So what other groups are axial and up with this CH3? Which carbons are they on? Right, a 1, 2, 3. It's called the 1,3 diaxial interaction. So 3 carbons away, there's an H that's axial. So that's going to bump into this. 1, 2, 3. There's another H that's axial that's going to bump into it. So all they want you to do is to highlight these 2 H's. They wanted you to highlight them essentially here. But you had to do the ring flip to realize which ones are going to be diaxial with it. You see that? So big groups don't want to be diaxial, right? So if you had to look at these 2 conformations here, right? These are 2 conformations. Which conformation do you think is more stable? A or B? So you should be looking at the things in the axial positions. Everything that's axial, right? We want that stuff to be out of the way. Which one do you think's which conformation do you think's better? A or B? Better has less interactions, right? So the bigger groups are equatorial, right? You want the big groups equatorial because you don't want things running into each other in that diaxial interaction. If I had to guess, what's the biggest element in the whole business here? Which one's the biggest? Which element's the biggest of all of these? Bromine. So which one has bromine axial? A does. So I would guess that this is maybe the worst because bromine's so big. That could be an argument. Bromine's so big. Let's make sure bromine's equatorial. So it doesn't run into, in this case, the H and the fluorine. Am I positive on that answer? No. If I ask you a question like that on a test, I'd make it much more clear. But you can look for, right, you see what I'm looking for, right? The 1, 2, 3 diaxial interactions. And it happens on both the top and the bottom part of the rings. Another Newman projection problem. This is chapter 3, number 26. So in this case, we're going to start with a Newman projection and be asked to draw it into a 3-dimensional Sawhorse, Wedge and Hatch type problem. So F, H, Br, Cl, CH3, and OH. So for this case, we need to imagine, right, now we're looking down this, and we see the bromines to my left and the CH3s to my right. We need to be able to draw that now with wedges and hatches. And how are we going to do that? How can we do that? So I like to first claim where my eyeball is going to be. In this case, I'm going to put my eyeball right here. All right, so that means this is what I'm looking at, this carbon right there. So if I label this carbon 1, this is carbon 1 right there. All right, so if I'm looking at carbon 1, what do I see? What's on my left-hand side? What's to your left in carbon 1? Bromine. So and if I'm going to turn myself, right, to the right here, the bromine is going away from me, so that's hatched. All right. What's coming out at me? What's to my right? Is going to be a CH3, hopefully. Right? Then what's straight up above me? The fluorine is. Good. Now if I keep looking down carbon 2 here, and there's 1 and there's 2, what do I see on carbon 2? Where's the chlorine at from where I'm looking? It would be straight down, right? There's the chlorine. What's to my right on carbon 2? So to my right would be the OH. And then going away from me would be the H. A quick way to check yourself that you didn't mess up. Right? The H and the bromine, are they on the same side? Yeah. So if the bromine's wedged, the H better be wedged too. The OH and the CH3, are they on the same side? Then they better both be on the same side in the way you drew it. If the fluorine and the chlorine are both in the plane, then they better be right up down the middle. So it's a good way to check yourself to make sure you did it right. Practice, practice, practice. Use your model kits. All right, taking a look at another nomenclature problem, which is going to introduce a new substituent or functional group name. So again, here we try to find the longest parent chain. So hopefully we can do that. That's this guy. All right. And again, we need to decide how we want to number it. And in this case, does it matter which way we number it? We only have one substituent. This is our substituent here. And so it's going to be 3 either way, right? So our parent chain is what? It's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. That has to be 4 either way. Ooh. Right? 4 either way. No matter, I can't do it any different, right? So it's 7, which is what? Heptane. So what do we call that substituent? So it's a 3-carbon group, right? A 3-carbon group, right? And this means what it's attached to. We call that an isopropyl. So this 3-carbon piece is an isopropyl group. So how we name it? We would name it 4-isopropyl heptane. So you need to know what an isopropyl group is.
So what would be like try?
You could name it without using isopropyl, but then you'd have to use parentheses and things get a little weird. So you should know what isopropyl is. You'll see it a lot. All right, let's look at a series of Newman projections and judging them by their potential energy. So let's take the compound 2-methyl butane. So it's a 1, 2, 3, 4, 2-methyl butane. We want to think about what this looks like in a Newman projection. So usually when they give you these these four kind of carbon pieces, what they want you to do is usually look down C2 and C3 to see what it looks like. So if I number these carbons, 1, 2, 3, 4, right? What they're going to want you to do, your eyeball is basically going to be looking down 2 and 3, right? You can look down 1 and 2 or 4 and 3, but there's hydrogens there, and that's not that interesting, right? So in this case, since they don't necessarily tell us, right, the wedges and hatches here, we can just kind of make it up, right? It doesn't really matter. So if I drew a Newman projection here, and I told you the carbon we're looking at, right, is carbon 2. What's on carbon 2? What things are on carbon 2? A methyl and a H, right? We don't draw the H's in. Carbon 2 has an H on it. What about carbon 3? It has that carbon 4 and then 2 more H's, right? We just don't draw them in. So are they going to be important for this? For sure. So this one's kind of really, it's just kind of easy. As long as you have the right things on there, you don't need, right? We're not even worried about the wedges and hatches here. You just need to put the right things on carbon 2. So what does carbon 2 have on it? It has carbon 1, which is a CH3. So that's carbon 1. We have another CH3 that I didn't label. And it also has an H, right? What does carbon 3 have on it? It has an H, and a CH3, which we've called carbon 4. Now, because there's no wedges and hatches, I can just put them wherever, right? I obviously had to make sure carbon 3 had the 2 H's and carbon 4 on it, but did I care about left and right, up and down? No. If you're not shown wedges and hatches, you don't have to worry about it. So now the second part of this question then, what it wants you to do is essentially take this Newman projection and start rotating 60 degrees, start rotating one of the carbons 60 degrees, and start finding the energy differences. Like, well, how high in energy would this one be versus an eclipsed one versus another staggered one, right? So what you want to do now is to start rotating carbon 2 60 degrees. So right, this is a staggered conformation. So all staggered conformations are always lower in energy than eclipsed conformations. Right? Eclipse is when the things are on top of each other. So if I did one example for you here, I did a 60 degrees rotation. Which carbon do you want to move? The front one or the back one? Doesn't really matter. Which one do you want me to keep still? 2 or 3? Keep 3 still? All right. So if 3 is staying still, I can draw in the stuff on 3 without worrying about it, right? Should we rotate clockwise or counterclockwise? Clockwise. So 60 degrees clockwise. That means, right, this H is rotating to the right, right? Everybody's rotating to the right. So now the H from carbon 2 is now going to be on top of the H from carbon 3. The CH3 is now there on top of that H. And over here is the other CH3 now on top of carbon 4. So this is 4, this was 1. And this is an eclipse conformation, which obviously is going to be higher in energy than, right, a staggered. And in particular, this is really bad because I got 2 CH3s on top of each other, right, which is way bad versus just 2 H's. So this one would be pretty high in energy, for sure. So you would go on and do this a couple more times. The biggest thing here is, right, which of these, if you have an eclipse conformation, it's obviously going to be higher in energy than a staggered. Right? So make sure you take a look at your charts when they show these things. Right? If your graph says potential energy, right, the eclipse things should be higher than the staggered things. Right? So as you rotate, you'll change the potential energy. So now we're switching gears a little bit with the nomenclature, but with an alcohol. So when we name alcohols, we need to include in the longest parent chain the actual OH. So the key here is we need to have the longest parent chain, but with the OH. right? So we can't have something that doesn't have the OH. So that's the one thing you kind of got to be careful of. So looking here, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we could go that way. There's 2 8s. 1, 2, 3, 4, 5, 6, 7. So it looks like we could either go this way or we could go this way. How do we decide which way to go is tough. But again, we're back to thinking about, right, the OH and what could be, which chain would have the lowest numbered substituent. If I numbered this way, I'd have 1, 2, 3, and now there's a methyl group on 3, right? If I go this way, it's 1, 2, 3, 4. So this is lower. Let's go this way then, right? Everybody see how we could have gone this way, but that wouldn't give us a lower number substituent. So we'll go this way. And the way we're going to number it, right? Again, now we have another question. Do you want to number it this way, left to right, or right to left? Because again, 1, 2, 3. 1, 2, 3. So that's a tie. 1, 2, 3, 4 for the OH versus 1, 2, 3, 4, 5 for the OH. So we should go from right to left. So 1, 2, 3, 4, 5, 6, 7, and 8. So our parent name is a octanol because it's an alcohol. So we have an octanol, right? Alcohol, and 8 carbons. What's on there? We have a 3-methyl and a 6-methyl. So we'd have a 3,6-dimethyl. And I think that covers everything, right? Oh, nope, no, it doesn't. Yep, what's on carbon 4? What's on carbon 4? We're missing something there. What's that? That's 3 carbons, so that's 4-propyl. Right? 4-propyl. So it should be 3,6-dimethyl, M before P, 4-propyl, octanol for the alcohol. 4-propyl is just because it's off 4 and it's 1, 2, 3 carbons. And P is after M in the alphabet.